All right, I hope you guys are doing well today. This lecture is going to be on resistor combination techniques, which should largely be a review of what you guys learned back in the Engineering 120 series. We're going to get into a little bit more detail about the reasoning why resistors combine the way that they do. But before we do that, does anybody have any questions about any of the previous in-class assignment problems or any of your homework problems that you would like me to look at? Jordan Grayer asked about ICA number 3, problem 3. So let's address that really quickly. All right, so ICA problem 3, number 3. Okay. So you're given a particular circuit, and the only pieces of information that you are provided are the voltage, the current flowing through the 22 ohm resistor, and then the resistor values themselves. You are asked to use Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law in order to determine the power supplied by the voltage source Vs. So if our ultimate goal here is to calculate the power supplied by our voltage source, then we need to know two pieces of information. We need to know what the voltage drop across the voltage source is, which is the value of this voltage Vs here, which we were not provided. And we also need to know the value of the current that's flowing into the negative polarity terminal of our voltage source, which I'm going to call IS, like so. Because we should know from our second class meeting that whenever we have the current flowing into the negative polarity terminal of an element, that gives us, or I times V gives us the supplied power, okay? So we need to figure out how to solve for both Vs and Is for this particular circuit, okay? So let's take the information that we were provided and see what we can do with it, okay? So we know that the current flowing through the 22 ohm resistor is 145 milliamps. So I could say then that this voltage right here, which I'm going to call V22, can be found using Ohm's law. So that's just going to be V is equal to I times R, because the current is flowing into the positive polarity terminal and out the negative polarity terminal of the 22 ohm resistor based on the polarity of the voltage that I chose. So that's going to look like 145 milliamps times 22 ohms. And if I throw that into my calculator, 0.145 times 22 gives me a voltage of 3.19 volts. Okay. Since our 22 ohm resistor and our 17 ohm resistor are in parallel, if there is a voltage drop of 3.19 volts across the 22 ohm resistor, there is also a voltage drop of 3.19 volts across the 17 ohm resistor, okay? So if that's 3.19 volts, then this is also 3.19 volts. We can use that information to find the current flowing down through the 17 ohm resistor, which I'm going to call I17, like so. So using Ohm's law, I17 is going to be 3.19 volts divided by 17 ohms, which I get to be 187.647 milliamps. Okay. So now that we know the current flowing down through the 22 ohm resistor and the current flowing to the right and down through the 17 ohm resistor, we can apply Kirchhoff's current law at this node in order to find that unknown current IS. So I could say that IS, which is the current flowing into the node, has to be equal to IX plus I17, which are the two currents that are flowing out of the node. So when I add those two guys together, I wind up getting that the current that's leaving the positive polarity terminal of my voltage source is 332.647 milliamps. Okay. I can use this information to determine this voltage, V11, just using Ohm's law. So V11 is going to be 11 ohms times that 332.647 milliamps. Which comes out to be 3.659 volts. And then lastly, I can use, let's see, Kirchhoff's voltage law around this path to find Vs. Okay, so that would look like negative Vs plus V11 plus V22 is equal to 0, which I could rearrange as Vs is equal to V11 plus V22, or 3.659 volts plus 3.190 volts. And when I add those guys together, I get a voltage of 6.849 and some change volts. And now my power is simply Vs multiplied by Is, or 6.849 volts multiplied by 332.647 milliamps. And I get that to be 2.278338 and some change. I'm just going to leave it at 3 decimal places watts, which is indeed the answer that you were provided. Jordan, was that explanation sufficient for you? All righty. Any other questions before we move on to resistor combination techniques?
For this problem, could you combine the parallel circuits and then do the same thing through it? Which I know isn't part of the problem, but that's just kind of how my brain went with it.
So the short answer is yes, but I don't know if it would. So if you combine those two parallel paths, which we technically haven't covered yet in this class, we're going to do that today. But if you combine those two parallel paths, so meaning specifically the 22 ohm resistor and the 17 ohm resistor, that could be beneficial depending on when you chose to do that. And so what I mean by that specifically, and I'm not trying to be, cryptic or weird, is if you combine those two resistors before you calculate that voltage, V22 or anything like that, then you actually lose information, because the current IX is defined as only flowing through the 22 ohm resistor. So if you combine those two resistors into a single equivalent resistance, which again we'll talk about here in a couple of minutes, that IX goes away because that 22 ohm resistor no longer really exists as far as we are concerned. So the only thing we have is an unknown voltage and then two resistances. We don't know any currents. We don't know any other voltages, so we don't have enough information to actually solve the problem. If we do that combination after we find that voltage V22, um, knowing the total voltage drop across those parallel resistors, we could divide that by the equivalent resistance, and that would be a slightly different way to get that current IS. But it should give us the exact same result as what I did by just applying Kirchhoff's current law at that node I circled in green. So,
Understood.
yeah. Any other questions?
Yeah, I had a quick question about problem number 5 on the first homework.
So let me pull that up real quick like. Okay, so first I'm going to apologize to you and anyone else that struggled with this problem because it is worded poorly, okay? And so what I mean by that specifically, let me pull this window over so that you guys can see it, okay? So hopefully you all can see the problem that's being asked about. So it asks which of the DC sources above are supplying power. What it means is which of the DC sources above are supplying positive power, okay? So for example, if we look at this voltage source here, V1, hopefully you guys can see my cursor moving around and all of that kind of stuff. The current I2 is flowing into the negative polarity terminal because we see that it flows out the positive polarity terminal. So V1 times I2 is supplied power. However, we only check the box if the product of those two numbers is actually going to be positive, which in our case, V1 is negative and I2 is positive, so we wouldn't check that box. So because V1 is supplying negative power. Now let's look at this current source I2. So the current is flowing into the positive polarity terminal. So what we want is for negative I2 times V2 to be positive. Another way to think about that is that we want one of either I2 or V2 to be negative, okay? So since V2 is a positive quantity and I2 is a positive quantity, that guy is absorbing positive power, which is not what we want. So we wouldn't check the box for I2 either. Moving along to voltage source V3, we have the current I3 is flowing into the negative polarity terminal. So we want I3 times V3 to be positive. Well, V3 is negative and I3 is negative. So when we multiply those two guys together, it's going to be positive. So we would check the box for V3. Looking at current source I4, because it's in parallel with this voltage source V3, the current is flowing into the positive polarity terminal, out the negative. So I4 times V3 is absorbed power. So we want I4 times V3 to be a negative quantity. I4 is positive, V3 is negative, so we have negative absorbed power, which is the same thing as positive supplied power. So we should check this box. Moving on to voltage source V5, the current I6 is flowing into the positive polarity terminal, out the negative polarity terminal. So I6 times V5 is absorbed power. So we have negative current times positive voltage. So we have negative absorbed power, which is the same thing as positive supplied power. So we check that box. And then lastly, we have the current I6 is flowing into the negative polarity terminal of V6. So we want the product of V6 and I6 to be positive. Since V6 is positive and I6 is negative, that doesn't work. So our answers should just be these three guys right here. And for what it's worth, I'm going to check it. And I was indeed right. So I think the overwhelming majority of the confusion that you guys have on this particular problem is, again, because it's worded and it says which of the sources are supplying power when it really means which are supplying positive power. Graham, was that explanation sufficient for you?
Yes, it was. Thank you.
No problem. Any other questions? All righty, well then let's get on to the topic of the day. So, resistor combination techniques. So, before we talk specifically about resistor combination techniques, I want to introduce you guys very briefly to the topic of electrical equivalence, okay? So let's say that we have some generic black box network. Like so. And a black box network like this just means that it's made of circuit components and we don't really know or care what's inside. So I'm just going to call this guy black box network number 1. Here are its terminals. And then way over here to the right, I'm going to introduce a second black box network, which I am going to unimaginatively name black box network number 2. And here are its terminals, okay? So let's say that I excite black box network number 1 with a voltage source, okay? So I'm just going to call this voltage source here VDC. And when we excite black box network number 1 with that voltage source, we can measure the voltage drop that appears across the terminals of the network, as well as the current that's flowing into the network. Okay. Well, if we were to excite black box network number 2 with that exact same DC voltage source, and actually let me call this V1 and I1, okay? So if we excited our second black box network and measured the voltage drop across its terminals, let's call this V2, and measure the current flowing into its terminals, let's call this I2, we can say that black box network number 1 is electrically equivalent to black box network number 2 if the voltage measured across the terminals of each network is the same, which means V1 must be exactly equal to V2, and both of these things have to happen simultaneously. The current entering the terminals of black box network number 1 must be exactly equal to the current entering black box network number 2. Okay. Another consequence of this is that the power absorbed by black box network number 1 would be equal to black box network number 2. But the easiest way for us to think of these things is if the voltage is identical and the currents are identical, then the two networks are electrically equivalent to each other. Okay. So what we're going to be doing here in a couple of minutes is we're going to be using this definition of electrical equivalence in order to figure out ways to simplify networks containing multiple resistors. Okay. But this is fundamentally the starting off point of any kind of circuit simplification we're going to do in this class. We always need to maintain electrical equivalence. Okay. So let's start by looking at a network containing resistors in series. Okay. So let's say as part of some larger circuit, I have a network containing some number of resistors connected together in series. So I'm going to call this resistor R1. This resistor here will be R2. And I'm going to go all the way out to some resistor R sub N, like so. Actually, let me put some ellipses there. So I'm kind of implying here that we could have any number of resistors connected in series if we're interested in something like that. Okay. So here is our network of N resistors in series. Okay. So I'm going to say that this network of resistors has some total voltage drop across it, seen between these two terminals that I've indicated, and I'm just going to call that voltage V. Okay. And similarly, there's going to be some current flowing into my network of resistors, and I'm going to call that I. Okay. And so what I'm going to do now is I'm just going to label the voltage drop across each of those resistors in my network. And I'm going to choose to put the positive polarity terminal such that my current I is flowing into the positive polarity terminal of each of these resistors. That's just going to make sure that when I use Ohm's law here in a minute or two, I'm never going to have to worry about any negative signs. So for what it's worth, whenever I don't know the polarity of a resistor, or it isn't given to me, I usually choose to put the positive polarity terminal in such a way that a known current is flowing into it, just so that my Ohm's law gets a positive sign. Okay. So I'm going to call this guy right here V1, this guy right here V2, and this guy right here V sub n. So if I apply Kirchhoff's voltage law around this loop, what I'll wind up getting is negative V plus V1 plus V2 all the way out to V sub n is equal to 0. And I'm going to choose to rewrite that as V, my total voltage drop, is equal to V1 plus V2 all the way out to V sub n. So the total voltage is equal to the sum of all of the voltage drops across the individual resistors. Okay. I got from that first step to that second step simply by moving that negative V at the front to the other side of the equal sign. Okay, so nothing wild or crazy here. Now what I'm going to do is I am going to use Ohm's law to express all of those resistor voltage drops in terms of that common current I. Since all of those resistors are connected in series, they all have the same current flowing through them, okay? So this would look like V is equal to I times R1 plus I times R2 all the way out to I times R sub n. And there's obviously a common factor of I in all of the terms on the right-hand side of the equal sign. So I'm just going to pull that out and then lump all of those resistors together. So that's going to give me I multiplied by a factor of R1 plus R2 all the way out to R sub n, like so. So from here, I'm going to define my equivalent resistance, Req, is just going to be the ratio of the voltage drop across the terminals of my network divided by the current flowing into the terminals of my network, which is exactly how resistance was defined in the beginning of our last class meeting. And in this case, if I take this expression for V and divide it by I, I'm left with just R1 plus R2 all the way out to R sub n. So my electrically equivalent resistor is just the sum of all of those resistors added together. Okay. In a more succinct form, I might use summation notation. So I could say that Req is the sum from I is equal to 1 to n of R sub I. Okay. So in other words, we have just used Kirchhoff's voltage law and Kirchhoff's current law to prove that when you have resistors in series, you just add their values together, which is exactly what you guys learned back in the freshman engineering courses. Okay, so we've proven this more formally so that you know where this comes from. Okay, so any questions about resistors in series before we move on to what happens when we have resistors in parallel? Alex S., you are unmuted, but I don't hear anything, so I just want to make sure you're not trying to ask me a question. You just muted yourself, so you're good to go. Okay. I wasn't hearing anything. I just wanted to make sure that you weren't asking something and I missed it. Okay. So now let's look at resistors in parallel. So once again, I'm just going to treat my resistor network as if it were part of some larger network. And in this case, I'm going to have N resistors connected in parallel. So here's going to be some resistor R1. Here will be some resistor R2. And then out here will be some resistor R sub N. Let me close my network down here on the bottom like so. And so this is the system that we're looking at. So once again, I'm going to say that the total voltage drop across the terminals of my network is V, and the total current flowing into the terminals of my network is I. And what I'm going to do now is I'm going to just label all of my resistor currents. I'm going to choose to have all of my resistor currents as direction down so that the current is flowing into the positive polarity terminal of each resistor. And my Ohm's law won't have any negative signs that I need to bother myself with. Okay. So let's call this current right here I1, this current right here I2, and this current right here I sub N. Okay. So if we apply KCL number 1 at our top node, so that's the current flowing in equals currents flowing out formulation for Kirchhoff's current law. Our current flowing into that top node is simply I. And the currents flowing out of that top node are going to be I1, I2, and so forth, all the way through to I sub N. So now I can express all of those resistor currents in terms of that common voltage V, because whenever we have elements in parallel, like all of these resistors, we know that they all share the same voltage drop. Okay, so using Ohm's law, this would give us I is equal to V divided by R1 plus V divided by R2 all the way out to V divided by R sub N. Once again, we have a common factor on the right-hand side of our expression, so I can simply factor that out. So continuing on down here, that would look like I is equal to V multiplied by a factor of 1 over R1 plus 1 over R2 all the way out to 1 over R sub N, like so. Well, I'm going to define my equivalent resistance, REQ, as the ratio of the total voltage across my network divided by the total current flowing through my network. And that's going to look like 1 over R1 plus 1 over R2 all the way out to 1 over Rn. I take the sum of those reciprocals, and then I take the reciprocal of that as well. So it's really just 1 over R1 plus 1 over R2 all the way out to 1 over Rn. In a more succinct form using summation notation, we would see that REQ, is going to be 1 over the sum from I is equal to 1 to N of 1 over R sub I. Okay. So this is the method for combining parallel resistances that you guys were introduced to back in the Engineering 120 series. I want to add a couple of more little things to think about for us now that we're in kind of a higher level class, okay? So let's say that we had two resistors in parallel. So here's some resistor R1, and here's some resistor R2, and we're trying to find the equivalent resistance of that combination, okay? So according to the method that I just showed you guys, we could say that Req in this case would be 1 over R1 plus 1 over R2. So before I move on from here, does anyone disagree with that statement? All right, nobody is saying that they disagree, so I can only assume your silence indicates agreement. So what I'm going to do now is I'm just going to play around with this relationship with a little bit of algebra, okay? So the first thing that I'm going to do is I'm going to multiply that factor of 1 over R1 by a factor of R2 over R2. Because R2 is, R2 over R2 is just a fancy way to represent the number 1. That's perfectly legal, right? Very similarly, I'm going to multiply that factor of 1 over R2 by a factor of R1 over R1. And once again, that's just a fancy representation of the number 1. So what that did is it gave me a common denominator of R1 times R2 in the denominator of this overall expression. So I could kind of simplify this thing. So I know that I'm going to have R1 times R2 in the denominator. Since the denominators are the same, I can just add the numerators together. So that's just going to be 1 times R2 plus 1 times R1. I'm going to choose to write that as R1 plus R2. And this whole fraction is below that 1 over thing there. So lastly, now I have 1 divided by a fraction. And hopefully we all remember from our high school or middle school algebra classes or whatever, that whenever I divide by a fraction, that's the same thing as multiplying by the reciprocal. So I can really just turn that bottom part upside down, and that leaves me with R1 times R2 over R1 plus R2. So this is a shorthand method for calculating the equivalent resistance of two parallel resistors, okay? It only works in this particular form with exactly two resistors, okay? So if you had 3 resistors, it would not be R1 times R2 times R3 over R1 plus R2 plus R3 because the units don't work out. You would have resistance cubed over resistance is going to be in ohms squared, which is not the units of resistance. So that should be an indicator that you can't do it that way in particular. Okay. Some of you may have been introduced to this method back in the Engineering 120 series. Others of you may not have been. It really just depends on who you had as your teacher. So I want to make sure that you're all aware of it now because I'm going to use this particular method for combining parallel resistances far more often than I use the 1 over the sum of the reciprocals method. Mainly because I'm lazy and I can type this into my calculator faster. You do whatever you're most comfortable with. I just want to make sure that you're aware of this because I use it so often. Using this relationship, I now want to bring to your attention a couple of special cases, okay? So what happens if R1 is equal to R2? Okay. So whenever we have two resistors that are identical to each other and they are in parallel, using our expression we defined above, we would have R1 times R1 over R1 plus R1, which is just R1 squared divided by twice R1. And we can see very easily that the squared gets rid of this guy down here in the denominator, and we are left with simply R1 divided by 2. So essentially, anytime you have two identical resistances in parallel with each other, the equivalent resistance is just half of whatever the original resistor value was. So two 10-ohm resistors in parallel looks like a 5-ohm resistor. Two 1,000-ohm or 1 kilo-ohm resistors in parallel looks like a 500-ohm resistor, and so on and so forth. You just take whatever resistor value you were given and multiply it by a factor of 1/2. That's your REQ, always whenever you have two identical resistors in parallel. Okay. Another special case that we can look at is what happens if R2 is equal to 0. So essentially, what we're looking at is what happens when we have some resistance in parallel with a short circuit. So I'm actually going to make a note here. That explicitly spells this out. So this is the case that we're going to have, okay? So using my R1 times R2 over R1 plus R2 representation, if R2 is 0, then that's going to give us R1 times 0 over R1 plus 0, which just comes out to be 0 ohms, okay? So essentially, anytime we have a resistor in parallel with a short circuit, the resistor doesn't matter at all, okay? It's just going to look like the short circuit by itself, okay? The reason for that is essentially given to us by Ohm's law, right? And so what I mean by that is if we have a resistor in parallel with a short circuit, what we will observe is that all of our current in that network will flow through the short and bypass the resistor that was in parallel with the short in order to make the voltage drop across both of those things 0, because as we know, the voltage drop across a short circuit is by definition 0. And whenever we have a resistor in parallel with a short circuit, the voltage drop across that resistor must be 0 because the voltage drop across two things in parallel have to be the same thing. Okay. So these are a couple of special cases that I just wanted to bring to your attention because we will also see them pretty regularly. So it's useful to not have to really think about it over and over again. Once we understand this and can accept it well, we can just directly apply these things. So what I'd like to do now is look at an example problem. And this example problem is going to be relatively complicated. And I want it to be kind of complicated because I want to show you guys how I approach a resistor network that it isn't obvious how everything is connected to each other, okay? So let me scroll down here a little bit. So this is really a problem from your web work. So this is homework number 3, problem 2, okay? And I'm just going to draw the network that you guys are given. So let's say that we're interested in this guy here. So this is going to be a 100 ohm resistor. Then over here, we are going to have a 50 ohm resistor. And over here to the right, we are going to have a 75 ohm resistor like so. Across the top here, based on my numbers, this is going to look like a 60 ohm resistor. Here we have a 76 ohm resistor. Down here we have a 25 ohm resistor. Down here we have a 200 ohm resistor. And then lastly, we have two diagonal resistors to take into account as well. So this guy is going to be 66 ohms. And this guy over here is going to be 150 ohms. And then you also have a couple of nodes labeled with letters. So this top right node is going to be A, top middle is B, top left is C, and bottom middle is D. Okay. So this is a fairly complicated network of resistances. And so my first step, whenever I see something like this where I can't intuitively just look at it and know what's going on, is I like to identify all of my nodes using different colors. So I'm going to say that node C is here in red. And I'm going to put node B here in green. Node A over here will be in blue. Node D down here will be in orange. And I can see that I have two other nodes that don't have a label. So I'm going to do this, goodness gracious, sorry. I'm going to do this guy in purple over here at the bottom left. And I'll give it a label of E here in a moment. And then I'm going to do this guy over here to the right in brown, and I'm going to call it F. Okay, so here's E, and here is F. So for the homework problem, you are asked to find the resistance seen between nodes A and B, the resistance seen between nodes B and D, and the resistance seen between nodes C and D. I'm going to work one of these with you today, okay? So somebody tell me, let's call this A, B, and C. Somebody tell me if we're working option A, option B, or option C, please. Just pick one arbitrarily.
A.
A. Thank you, Graham. So we are going to find the resistance seen between nodes A and B, okay? So I am a child of the 80s, and I grew up watching a TV show called Pee-wee's Playhouse. And on Pee-wee's Playhouse, they played a game called Connect the Dots. And so that's literally what I'm going to do with these resistors, is I'm just going to play Connect the Dots, where each of my dots is one of my nodes, and the path that is connecting the dots is going to be one of my resistors, okay? So on the left-hand side of the page, I'm going to put node A. And over here on the right-hand side of the page, I'm going to put node B. And my goal is to now connect those two dots with all of the resistors that I see on my original circuit diagram. I tend to start with the easiest path first, and then just keep working my way through things until I have all of the resistors taken into account, okay? So for me right here, the easiest way for me to get from A to B is directly through that 76 ohm resistor. So I'm going to put the 76 ohm resistor here in the middle, and that is one path that I can take to go from A to B. And I'm going to put a little check mark here above the 76 ohm resistor to remind myself that I've already taken that one into account, and so it shouldn't show up again. Okay? Now, a different way that I can get from A to B is to go from A to D to B. So I'm going to choose to put node D here directly in the middle. To go from A to D is the 150 ohm resistor. So that's this guy right here. And then to go from D to B in the most simple path, that's going to be this 50 ohm resistor. So now I need to find out if there's a different way for me to go from A to D. And there is. I can go from A to F to D. So that would look something like this. So from A to F is this 75 ohm resistor. And then from F to D is this 200 ohm resistor. So I've effectively got the right-hand side of the circuit sorted out now. So now I need to think about the left-hand side and the different ways that I can get from D to B other than the 50 ohm resistor that I've already taken into account. So the shortest path is probably to go from D to C to B. So I'm going to put C here in the middle, and I'm going to go from D to C using this 66 ohm resistor. And then I'm going to go from C to B using this 60 ohm resistor. Like so. And then now I can see that there is an alternative path for me to go from D to C. So instead of going directly through the 66 ohm resistor, I could instead have gone from D to E to C. So I'm going to put E here. So from D to E is the 25 ohm resistor. And from E to C is the 100 ohm resistor. Okay. And so now I've taken into account all of the different resistors and all of the different possible paths that I could take. I want to make sure that you all understand that each resistor is only going to show up once, okay? So all of my resistors have been accounted for. So with this form, now I can easily see which elements are connected in series and which elements are connected in parallel and so on and so forth. So I tend to start from the bottom and then work my way up this kind of ladder representation of what's going on. until I get down to a single equivalent resistance. So starting at the bottommost rung of the ladder, the first thing that I see is the 25 ohm resistor in series with the 100 ohm resistor. So I'm going to replace those two resistors with a single equivalent resistor having a value of 125 ohms. Is everybody okay with that simplification? So from here, I can now see that my 125 ohm resistor is in parallel with that 66 ohm resistor. So in my calculator, I'm going to do 66 times 125 over 66 plus 125, and I wind up getting 8,250 over 191. I'm going to leave it in that fractional form. And so I'm going to replace those two resistors connected between D and C with a single equivalent resistance also between D and C, having a value of 8250 over 191 ohms. Now, that new equivalent resistance is in series with the 60 ohm resistor, so I'm simply going to add my previous answer to 60. So that gives me a resistance of 19,710 over 191. That result is in parallel with the 50 ohm resistor. So I'm just going to do in my calculator answer times 50 over answer plus 50. And I get 33.68079. So let me erase those guys and replace it with a single equivalent resistance. 33.681 ohms. And I can't really simplify that right-hand bottom part anymore. So now I'm going to shift over to the left, right? So between A and D, I see 75 in series with 200. So that'll look like 275. And now I see that that 275 is in series, or excuse me, is in parallel with 150. So I have 275 times 150 over 275 plus 150. That comes out to be 1,650 over 17. So now I can see that the equivalent resistance between A and D is in series with the equivalent resistance between D and B. So I'm just going to add those results together. So I saved that 33.681 thing in my calculator earlier, so I won't get any rounding error. When I add those two numbers together, I get 130.7396 and some change. And then now I see that that 130.7396 equivalent resistance is in parallel with 76. So I'm going to do answer times 76 over answer plus 76 in my calculator. And I find that the equivalent resistance seen between A and B, if I haven't made any mistakes, which I don't believe I have, is 48.0 0.6147. So let's call that 0.61 ohms. Okay. So that is my process for combining resistors when it's not obvious to me how things are connected. Okay. You can do whatever you feel comfortable with. So if you learned a different way or something like that in the Engineering 120 series and it makes sense to you, that's great. This is the way that I do it. Even though I've taught circuits for 8 years at this point, I've, got a bachelor's and a master's and a PhD in electrical engineering. This is literally how I still do it to this day. So hopefully it helps some of you guys out. Before we move on to a last little thing, does anybody have any questions about that previous example or any of the stuff that we've talked about today? All right. Well, the last thing that I want to do with you guys is show you how being able to combine resistances and stuff like that can actually help you with your circuit analysis, okay? So I'm going to show you it as a circuit simplification tool to some extent. So let's say that we have the following circuit, okay? I'm not going to give you anything too wild or crazy here. So let's say that we have something like this. Okay. So maybe this is a 12-volt source connected to a 100 ohm resistor. Here we have a 50 ohm resistor. This will be a 75 ohm resistor. And this will be a 25 ohm resistor. And I'm interested in figuring out the current flowing through the 25 ohm resistor. Okay. So we could, if we were so inclined, kind of, well, there are multiple different ways that we could approach this. We could find the equivalent resistance of everything and then use connected to the 12-volt source and then try to use some combination of KVL and KCL and Ohm's law and kind of work our way around things. But I'm going to try not to just straight up throw the kitchen sink at this and see if we can approach it in a more formulaic form. Okay. So in our last class meeting, we had circuits where we had single loop circuits where everything was connected in series, and they were pretty easy to analyze. And we had circuits where everything was connected in parallel, and they were also pretty easy to analyze. So ultimately, my goal is to try to make this circuit look like one of those two and then glean what information I can from that, okay? So I'm never going to be able to make that 12-volt source not in series with that 100 ohm resistor. So I'm going to try to simplify this down to something where I only have things connected in series, okay? So in order to do that, what I'm going to do is I'm going to find the equivalent resistance of everything to the right of this dashed red line. Okay. So what I'm looking for, essentially, is REQ for this network. So here's a 50 ohm resistor. Here's a 75 ohm resistor. And here's a 25 ohm resistor. Okay. So can one of you tell me how I might find the equivalent resistance of that network?
You can do 75 plus 25, and then you can do, which is just 100, and then 100 times 50 over 150.
Exactly right. So the series combination of 75 and 25 in parallel with that 50 ohm resistor. Okay. So REQ would look like 50 times, actually, let me do it as 50 ohms. Units are important. Sorry, my penmanship is getting shitty. Over 50 ohms plus 75 ohms plus 25 ohms. Okay. Where I'm just using that parallel, R1 times R2 over R1 plus R2. But my R2 in this case is the series combination of 75 and 25. So I'm just treating that as if it were a single equivalent resistance of 100 ohms, which is exactly what Colin suggested. Okay. So if I throw this into my calculator, I'm going to do that really quickly here. 50 times 100 over 50 plus 100 gives me an equivalent resistance of 100 over 3 ohms. Okay. So I'm going to redraw my circuit down here. And I'm replacing everything to the right of that dashed red line with that equivalent resistance that we just found. Okay. Now, in doing so, I lost that current I-25 that I was interested in because I don't see that branch containing the 75 ohm resistor and the 25 ohm resistor anymore. So what was the purpose of me combining those resistors together? Well, the short answer is, with this new electrically equivalent circuit, it's actually pretty easy for me to find this voltage, which I'm going to call Vx. In my original circuit diagram, that voltage Vx would be right here, where it's the voltage drop across the 50 ohm resistor, and it's also the voltage drop across the series combination of 75 ohms and 25 ohms. Okay. So finding this voltage Vx will allow me to solve for that current I-25 pretty easily, because I-25 is just going to be Vx over 100 ohms, okay? So lumping all of those resistors together, even though I lost the thing that I was looking for, allows me to find a critical piece of information that I can kind of plug back into my original circuit to find the thing that I'm actually interested in. So we would find Vx by essentially just using Ohm's law, where I'm going to have a total voltage drop of 12 volts over, that's wrong. I'm going to call the current, sorry, I was about to do voltage division, which we haven't learned yet, so my apologies. I'm going to find this current, which I'm going to call Ix, first. So IX is going to be 12 volts over 100 ohms plus 100 ohms over 3. Let me get that in my calculator real quick. So that comes out to be 9 over 100 amps. Using Ohm's law, Vx is then Ix times 100 over 3 ohms, which comes out to be 3 volts. And then finally, the I-25 that I was actually interested in is then just going to be Vx over 75 ohms plus 25 ohms. So 3 over 100 comes out to be 30 milliamps. Okay. So this circuit would be a lot harder to analyze, or it would involve a lot more steps if we just threw KCL, KVL, and Ohm's law at the original circuit and tried to figure stuff out. Using resistor combination techniques allowed us to simplify just parts of the circuit that we were interested in order to find pieces of information that we could have used to find what we were actually looking for, okay? So resistor combination is a lot more useful than just finding the REQ for the sake of finding REQ. So I just wanted to make sure that you guys understood that in the context of analyzing a circuit. All right, thank you guys for your attention today. I don't really have anything else that I would like to talk about. If you have any questions or anything, I would be more than happy to answer them. If not, work on the ICA or enjoy the rest of your afternoon. You're adults, you can do whatever the hell it is that you want. I'll hang out on Zoom to answer any questions that you guys might have, but if you choose to dip, I will catch you later.